Okay, so we're going to talk today about this Safari board. Some of you have heard about it, and basically it's a board we designed here at the ESC. So here's the agenda. We're going to talk about the board. What is it? What can it be used for? Why did we even make this in the first place? Some features, and then the main chip that's on it, the IC. It's an analog front end. The configurability of this board and chip through software and hardware. Then we're going to talk about the kind of the main focus maybe is this FAE Demo Kit. So we have 10 of them, and these are available from Test Drive. You can bring them to your customer or show them to them over the phone, or actually I even made filmed a video of this, so you could just show the video if you want to your customers. We're going to look at that. There is a customer demo, which is a scaled down version of the FAE demo. The FAE demos has a motor, and you have 3 sensors mounted and monitoring it. And the customer demo, we tell them to buy the boards and the sensors, and they run the same demo, just not on a motor. So then we're going to, Corey's going to talk about how to develop, how the customer might use this kit to develop their own solution. This was a last minute request of Perfecto, so sorry about that, Corey. This is how to do that. He's got some future projects coming up, and the main one is using it Jupyter Notebooks to do plots of the performance of these sensors. So, and then there's additional resources. Okay, so what is Safari board? So it's a multiple input analog front end, basically, and it doesn't just have to be used for sensors, but that's what we're using it for in our demo. And so let's talk about it. It's compatible with 96 board standard for mezzanine card, so it's a mezzanine card. Plugs into a 96 board motherboard. In the case of our demo, we're using the Novtech Meerkat, which runs a IMX7, you know, slightly older processor, but oldie and a goodie, right? This features the AD7124, the chip I just talked about, 24 bits. Has screw terminals all around the perimeter of the 3 sides. You can see the top is the low-speed connector that we use to connect to the Meerkat board underneath it, and you can see there's you could connect another board to this as well if you wanted to. There's an onboard precision voltage reference. Uses a SPI interface to communicate with the Meerkat. There's filtering on each input to anti-aliasing and you know, noise also. Since it's a sigma delta, it oversamples and it pushes the aliases further out, so you don't need like a brick wall response for the filtering. It's just a simple passive RC in this case. That's what we're using. And it filters common mode also, because you could be hooking up a differential sensor. There's a lot of test points on this. I don't know if you can see does this want to move or not? Can you guys see that cursor? Well, anyway, there's the test points.
Yeah, we can
all around it. Okay, what else? When you combine it with the 96 board, it's a complete analog sensor interface and convert to digital solution. So let's see, I'm trying to get this to turn. There we go. So here are some of the applications you could use it for: environmental sensing, industrial monitoring, instrumentation, temperature, pressure, you know, just a variety of applications that you would want, that you would hook up an analog, fairly low bandwidth, low speed sensor, you know, mostly slower changing signals. So why did we even make this board? I mean, there's eval boards out there already. There's an AD7124 eval board from ADI, uses a Blackfin processor and has a GUI you can control it with. So the reason we did this, well, first of all, ADI requested a board that showcased analog signal path. So, and this does that. And then, you know, Brian Hunt's unit, they wanted some kind of industrial monitoring, or they requested it. It wasn't, you know, they didn't insist on it, but they thought they'd be nice to have that. They wanted industrial monitoring, and our demo is an industrial monitoring application. So why do we use 96 boards? First of all, Aero's big in 96 boards right now, as you may or may not know. There's the Thor 96. There's a few others that I forgot the name of them right now. But so this helped. What the reason? One of the reasons was these other demos are, kind of engineers request them and stuff, but maybe they're not developed. They don't want to develop on a black fin. So this way you can get, it's a fairly, it's a small portable solution, and there is a community of 96 boards, like Arduino or BeagleBone or Raspberry Pi. Now, not as big as those, but there is a community that uses 96 boards. Now this runs Linux, open source, and you know all about Linux. So that's a nice, a convenient thing for developing. Customers want to develop with this, and it uses an ARM processor to do that. Here's a few other 96 boards that are out there: the AML, Thor 96, Shield 96, Avenger. You probably heard of all these. So let's look at the chip. Here's the chip. It's there's the block diagram. Kind of looks like many analog front ends. It's 8-channel, 8 differential inputs can go in. It's 8 channels, low noise, low power. So it has 16 inputs, 24-bit sigma delta, samples up to 19.2 kilosamples per second. Now, because this is a sigma delta oversampling converter, as I mentioned, you can't just divide 19.2 and get 9.6 kilohertz and say that's the bandwidth. It's not half of Nyquist. It's less than that. It's about 5 kilohertz is the maximum input bandwidth in its fastest mode, high power, using a Sync 3 digital filter. Has a gain, programmable gain with buffers, a programmable digital filter, Sync 3, Sync 4, notch filters, 50, 60 hertz, post filter. You can choose from a number of different references. The ADC, the chip itself has an internal reference, and then you can hook one of two. You can hook up 2 different references to the outputs and select which one you want for that. And you can actually even use the supply as a reference too. That's all software driven. There's a couple on-chip current sources. We use this in this case in order to drive an RTD temperature probe. So it puts current through the resistance. Then you measure the voltage and you can determine what the temperature is. And you can select between low, mid, and full power modes. It's got built-in diagnostics, all software configurable using a SPI interface. So, any questions so far?
I haven't seen any in the chat yet.
Okay. So let's.
You're doing good.
Okay. So here, let's look and see how is this configurable. It's been designed to help the person design using this board, help them get a solution. So here's the inputs in the little squares around the perimeter. Each of these connectors has power and ground, so that just for convenience of hooking up sensors, you don't have to have a lot of wires, 12 wires trying to share one screw terminal or going halfway across the board or anything. There's a choice of 2 external references, as I said, or an internal. You got some jumpers, a resistive divider on a couple of the inputs, and this allows you to use a higher voltage sensor, for example, and scale it down to be used by the ADC. And there's also use these jumpers to select between the onboard reference and an external reference. You power it from the 96 boards, which is transmitted through the low speed connector up at the top, or external supply. And so I chose 0805 size components because, they're still small, but they're not tiny. And this way you can change, let's say you want to change your filter, for example, your passive filter. Well, you could just hand solder these. And I've done changes with that. It's not too bad, not too difficult. And we've got all the schematics available, of course, for this. So here's the demo kit. And you can see the scale of it on the right compared to a laptop. So here's the block diagram. So we've got these 3 sensors we're hooking up to it, and they're used to monitor a motor. I'll show you a picture of that in a minute. Accelerometer, temperature sensor, and pressure sensor. And the pressure sensor is monitoring air being driven by a fan blade attached to the motor. And there's the block diagram of the Safari board. There's not a lot of chips on it, really. 807124 and some power and voltage reference. Then on the right is the Meerkat board, which is IMX7, and it has these different modules, Wi-Fi, UART. So what we're doing in this solution is we're going to push the digitized signal out across the UART through a UART to USB converter that I didn't draw here. And so the USB connection goes to your PC and you download some software onto it. And there's we did have a solution using Wi-Fi and AeroConnect, and the AeroConnect is not available right now, so we're just using the UART at this point, and we've kind of abandoned the Wi-Fi part of it. But somebody could do that. I just want to say that we did do put a lot of work into that. And to get this software, all you need is to run this demo. You get the kit and you download the software. So this is on an Aero GitHub site. Download it. Here's what the kit looks like. We have the Safari board. Underneath it is the Meerkat board. We've got a couple of NXP motor driver boards to drive a motor. There's a UART to USB board. And then for sensors, we have an ADXL203B accelerometer. This is actually their evaluation board. So it's mounted to a little tiny evaluation board, and we use that. It's a nice unit. RTD sensor taped to the motor, and a differential pressure sensor. You can see there's a tube right by it going to that fan enclosure right there, custom fan enclosure. And there's a blade mounted to the motor, but you can't see it right now. And we got a standard power supply and a 3-phase 24-volt motor we're using for this. Here's the signal path. Operating system, it's Linux, and the firmware used by the Meerkat to control signal flow and everything is on a SD card. So you put it into your Meerkat board, it loads it up, and then it sets all the registers within the ADC. The accelerometer, we're just showing one sensor. Accelerometer is, sending out data to the board where it gets digitized, filtered, digitized, etc. It gets sent by SPI over to Meerkat. And what happened? I'm going the wrong way. I'm sorry. And then the Meerkat sends it to our UART to USB converter board, goes to your PC. There's the plots. Here's what the plots look like. And you can see accelerometer, temperature, and pressure. And we have this motor cycling through 3 different speeds and then pausing and repeating. So you can see the 3 speeds here and the 3 quadrants of this accelerometer plot. You can see amplitude and frequency change. Now, it's not completely linear, especially at the low speed. You still got some vibrations, and it's not quite, you can't see as easily, exactly what speed it's going, things like that. Temperature is kind of interesting because the motor, as it spins, it heats up, but then the fan blade pushes air into the enclosure, it gets reflected back onto the motor and cools it down. And pressure is just dependent on that fan blade, which is dependent on the motor being driven. Here's the customer demo. Like I said, it's exactly like the FAE demo, just no motor. And we tell them to just get these components individually, and we have all the instructions on a wiki. Now we've got all this code is written in Python, and so now I'm going to turn it over to Corey to talk about that, and I can just turn the slides if you want, Corey.
Okay, before you turn it over, though, there was one question, Peter.
Yep.
What's the analog input voltage, right?
It's either 0 to 3.3 volts or 0 to 2. It's 0 to whatever your reference is. We've got an onboard reference and internal reference, both at 2.5 volts. You could actually also use the supply, which is 3.3 volts, powering the ADC. So you could do that as well. And there's buffers that allow rail-to-rail operation on the input. Any other questions?
Hey, Peter, this is Ryan.
Hey.
I mean, there's different, since it's a Dell SIG, I mean, there's different ways that you can extend the full-scale input range. So that 7124 is a super nice Dell SIG, different channels, different channel count and everything. It's a really, really nice part. If anybody needs to do precision stuff, then, you know, it works out really well. And so don't limit yourself just to 0 to, you know, the reference or whatever. So,
Peter, I think you can also run this part split supply because the analog front end is not ground referenced. So you can run it any as long as your voltage span doesn't exceed 5 volts, you can run it at like plus and minus 2.5.
I think you're probably right about that. I know you can with the chip for sure. You just gotta, you know, change a few things, decouple the bottom rail from ground. Okay, that's a good point. Any other questions?
Looks like Zephyr, you want to ask your question?
Yeah, so you're not doing any current sensing for the demo?
No current sensing, no, not at this time. There's a lot of possibilities. We just decided we had to pick something and try to, I thought about doing isolation on the inputs and just decided that we kind of keep it simpler and like Ryan and others have said, there's a lot of flexibility that you could put into this. It's meant to be a platform we develop with. Well, you know, that's all the connectors, test points, and things like that. So we made one specific demo for this, and we have the code for that. And then Corey's going to talk about a little about that, and then also how the customer could go on from there if they wanted to, you know, develop something using this board.
Okay, let's do it.
Okay, Corey, go ahead.
So everything is written in Python. So the GUI that Peter kind of showed off, that's written in Python and just converted to an exe to run on a Windows machine. And then there is, firmware is probably not the right word, but there's software that runs on the Meerkat itself that's also written in Python. The benefit of doing Python is that you don't have to compile it. You can kind of easily port it to whatever processor you want. And it's also a lot more kind of mainstream, and a lot of people are getting more comfortable with Python itself. So on the Meerkat, there's essentially an AD7124 driver, if you will, and that's kind of doing all your reads and writes. There's a config file that it reads. So think of like a big map of all the registers and all the settings and all the values. The Python driver just kind of reads through this configuration block and then sets the AD7124 up accordingly. So if, you know, a customer wanted to modify what channels are operational, some of the settings, want to change register bits, they could just, you know, open up a serial connection to the Safari board, Meerkat, make their changes, and then run the GUI again, which is kind of slick. The other thing is we are going to make the GUI code open source as well. So if you want to put another plot in there, you can do that. You know, change how you're plotting it, what library is using, any of that kind of stuff. The customer will be able to, you know, modify anything accordingly. So it might be better used as more of a reference. So like Peter mentioned, we're going to have customers buying the RTD probe and also the accelerometer. But let's say they want to buy, you know, a gyro or something else. It should be pretty flexible to kind of add that functionality. So what's on the next slide, Peter, is the Jupyter stuff. So we're also looking to, instead of running this as an executable, this GUI, right, that just plotting data from the Meerkat, we're looking to kind of bring it to Jupyter Notebooks. This kind of has the benefit of it's easy to hack at. So if I were to give you guys an exe file, there's not a lot you could do with it. You'd have to take the source, make your changes, recompile it, run it, and it's just not very user friendly. So what we're hoping to do is to take the GUI kind of as it is and with its plotting functionality, import it to Jupyter Notebooks, which is somewhat of a Python IDE. So the cool thing is that you can run code in place, you can put code in blocks, you can rerun everything, you can quickly modify. So if you want to add a plot, you can just copy the code block and add another plot. It's pretty straightforward. So we think this will give users the ability to quickly and easily modify it. You know, an exe is nice so you can't break anything, but if you want to tweak anything, it gets really difficult. So that's kind of the intent behind the notebook idea. So we're going to take the code we have today, bring it to Jupyter Notebooks, and hopefully it's a lot more user friendly for you and your customers.
All right, any questions on that? Here's some resources. We have Perfecto's got a nice site there with got with all the different ADI types of boards. And it's up at the top. And here's our links. There's a wiki for Safari. There's, of course, ADI's Engineer Zone. You guys know all about it. And then there's the link for the chip itself. So here's what the wiki page looks like. You can see the menu along the right side has links to all the different parts of it. There's schematics. There's detailed instructions. Also, I did a short video, like I was saying. This is something you could use to know how to run this yourself, and or you could just send this. You could just play this during a meeting with a customer, and it explains. It's less than 5 minutes actually. It explains how to run the demo and shows the results of that. Whoops, I guess that's it. So any other questions anybody have? So that's all I got.